Yo, yo! Dude, keyboard handling on Linux is pretty wild. We've been working on this Wayland compositor. Look at this bad boy. We've got two windows. We can resize them. We got input. Wowzer. And the next thing that I wanted to do was I wanted to do keyboard handling. So, like, how in this thing do I tell a window that I press the A key? Or, how do I type into an input box? What does my window manager have to do in order for an application to like get that information? And it turns out that this is like quite complicated, right? I don't know if it's actually that complicated in terms of implementation, but just trying to understand what the system is doing is kind of crazy. It's kind of crazy. So like where we start on this adventure is I open up the Wayland specification, and we've done pointer input before, so we have like a little bit of a clue of what's going on. You, as a person who sits down at your computer, you are assigned a seat, right? Theoretically, you could have like four people using the same computer, and they could all have their own window managers and stuff like that running with their own keyboards and their own mice, right? So everybody's assigned a seat. In basically every computer, you're only going to have one seat. And you see on this thing, you say, oh, we can get a keyboard from a seat. That sounds like the interesting part. And on this keyboard interface, when you look at this thing, it's a little confusing, right? When I press a key, the key is literally just like a number, a little uint. And you see that along with this thing comes a Wayland keyboard key map. And if you start like going down the rabbit hole of what the hell that means, I think I saw it in the Wayland spec keyboard here, maybe somewhere in here. They talk about the key map is a libxkb common compatible null terminated string to determine the xkb key code. Clients must add 8 to the key event key code. So like right off the gate, we're like, what the hell is going on? And so we kind of went down this whole path of trying to understand when I press a key on my keyboard, how does that make it down through my Wayland compositor. There's a bunch of stuff that happens like before my Wayland compositor, a bunch of stuff that happens after. There's this thing called libxkb common. Where do all the pieces fit together? And so I think we have a little bit of a picture of it now. I could very well have gotten this wrong because all of the reading that I've done about this was done in the past 2 hours, and we haven't written any code yet. So we could be wrong. But my understanding at this point is that there's a few pieces here, right? I have my keyboard. He is plugged in via USB into my computer, right? My computer is an operating system, has an operating system on him running Linux, and the USB, we'll skim over like the details of how USB protocol works and whatever, but somewhere the kernel has like an abstraction around this USB device, and he maps him as a USB human interface D, HID, human interface device, HID device, pin number. He's got some HID device, and we kind of poked around the drivers a little bit, and eventually found that the USB specification defines these low-level things called usage IDs. So in the USB specification, there is a concept of a keyboard, and the keyboard has USB usage IDs, and each of these IDs is like a specific letter, right? So if I have like the A key on my keyboard, that comes out as number 4. And we can actually find these if we run this program. Hold on. This program EV test. Hold on. I don't want you guys to see my password. That's secret sauce for me. But if I start looking at my keyboard and I start pressing like the A, S, D, F keys, we see that these have like scan codes, they call them, misnamed, I think, but they have these things called scan codes, and in here we can see like the lowest bits of this MSC scan thing, say 4 when I press the A key, and so we can start predicting, like if I press the G key, I should get A, so here we see an A here. If I press the P key, we should see 13 hex, which we do here. But these aren't really relevant for most applications. Most applications aren't looking at these like USB device codes, but they are looking at a higher level concept called a key code. So the Linux kernel, because he's not only using USB keyboards, he might be using PS2 keyboards or like Bluetooth keyboards. All of these guys, they have different ways of communicating the same information of like, I press this key, but like as a consumer of this thing, I want to use like the same interface. So Linux kernel, you plug in your keyboard, he goes, oh, there's a keyboard. Let me expose this as a dev input event handle or something. Dev input event, right? So these things are called evdev devices. Maybe we start drawing the picture. So we have this keyboard. This thing is USB HID, right? Then the Linux kernel converts this into like some sort of evdev device. Evdev exposes key codes. So what you can do, you probably won't, but what you could do is you could like open one of these files and just start reading it. And as you start reading it, every once in a while something will come out and he'll be like, oh, key A is here. Now, what's really confusing about this is that key A does not mean key A, right? So on my keyboard, I press the A key and it is the A key, right? Very lucky for me, I live in a like US English speaking country, and so my keyboard maps the expected keyboard very well. But if I were on like a German keyboard, we might see that on this guy, there's like a key on it with it that says O double dot on top, right? I don't know what it's called. I think somebody in chat said it's pronounced ule. I'm sure that that's not what they actually meant, but the ule key. This thing is where the semicolon would be on a normal keyboard, right? And so if you just scroll up on this HID spec from USB a little bit, which is not exactly the same as the key codes in Linux kernel, but we can maybe, assume that they're going to do something somewhat similar. They say, a general note on usages and languages. Due to the variation of keyboards from language to language, it is not feasible to specify exact key mappings for every language. So what they do instead is, one example is the Y key on a North American keyboard. In Germany, this is a Z. Rather than changing the keyboard firmware to put the Z usage into that place in the descriptor list, the vendor uses the Y key. So everybody just assumes that they're fucking North American keyboards, and it is software's job later on to map these things, right? So what we have is this guy, he says usage A. This guy says key A. But remember, key A does not mean key A. This means key A as in the location on a US QWERTY keyboard where the A would be. Right? So this is like, so far we haven't gotten into like really any software yet. This is all like, any like user space software. This is all like kernel driver shit. So now we kind of hit like this like user space boundary. So this is kernel user space. In here, we open the fdev handle, but that's not really good enough, right? Because we don't have, if I am an application, I want to type the letter A when somebody types the letter A, right? I don't want to have to think, oh, they press the A key on a keyboard. Am I a Dvorak keyboard? Am I a Swedish keyboard? Am I like a US English keyboard? What letter is that? And so that's kind of the job of libxkbcommon. Libxkbcommon. But we can't really use libxkbcommon yet because if we were to just open up that device handle and start outputting letters, this is where we'd use xkbcommon. But we are not in that case, right? We are actually a window in a window manager running on this system, right? So what actually happens is here we kind of have our like Wayland compositor. So on what we're seeing right now, this is like Kwin. And this Wayland compositor, he is going to actually probably go through this library lib input, whose job is like kind of to abstract away some of the like device quirks that you might see. So lib input will kind of open up this fdev handle and communicate the information of which keys were pressed back to the compositor through some API. But that lib input API is also going to work in key codes, right? So this is key code here, key code here. Now we're back at the part where we started, where we opened up this Wayland spec and we saw this like key map thing, right? So what happens here is, as far as I understand, this guy initializes some xkbcommon stuff. So he's also got xkbcommon here. And xkbcommon is kind of responsible for how these things translate into letters. But it doesn't go directly to letters. There's a few steps in here. So if I go into my KDE settings and I go in here and I click like, please make me Dvorak keyboard, right? If I just say I want English US Dvorak, and I like apply this, and I like go over here now and I type like ASDF, I'm actually getting AOEU, right? So immediately when I press this button, this is applied everywhere. We didn't quite get to like exactly how this is applied, but somehow someone is saying, hey, XKB common, like, could you please tell me all of the things that you support? And then he is somehow through like probably like a dbus API talking to the window manager and saying like, hey, Kwin, make sure that like all the applications that are running right now, could you let them know that we switched to Dvorak? And that's where this like key map thing comes in, is he's going to say, XKB common, could you like generate me a like descriptor of this thing that we can show to everybody? So I think that we have an example of that descriptor here, right? So like he's going to generate a string that looks like kind of like this. And the interesting parts here are at the very top, we see like these are on the right side are the numbers that Linux tells us. So these are the key codes, and this is how they map to like, you know, internal X11 key sims. Now you might say X11 key sims, why the fuck are we talking about X11? We're talking about Wayland. And you would be right. But because all software at some point was like written for X11 because Wayland didn't exist yet, this like idea of an X11 key symbol has like infected the whole Linux input stack. So what happens is we, as the compositor, we talk to lib input who's talking to evdev. So like the key is pressed, USB interface says, oh, he pressed A. Evdev goes, oh, that's key A. Lib input goes like, hey, you wanted to talk to like this keyboard that's plugged in for your seat where you're sitting? Yeah, he said key A. We go, I am the compositor. Did somebody tell me that I should be using some like weird key map or something? XKB, you, Mr. XKB library. I see that somebody pressed key A. Well, he actually kind of lies. He says somebody pressed key A, but let me add 8 to that because these XKB key codes are like exactly the same as the Linux evdev key codes, except they're just offset by 8 because at some point back in the day, the people who were making X11 were like, well, what if we need 8 more keys? Right? So they just kind of like reserved the first 8. So when you're using these things, you add 8 to every key you get from lib input before you ask XKB about them, which is kind of funny. But we go, hey, XKB, we've configured you in some way because somebody told me that I'm like an Icelandic Dvorak keyboard, even though it looks like a QWERTY keyboard on my desk. Could you take this key plus 8 and tell me what key sim it is? But really, you don't really care about the key sim. What you really care about is like the UTF-8 code point for that thing. And so then after you get the key sim, you ask XKB comment again for that thing. But I kind of lied a little bit. Really, what happens here is we're kind of missing like the connection to the client here. Client. So this client also talks to XKB common, right? But he only talks to XKB common from the perspective of the compositor has sent me the key map. So like, dude, those are letters. Map. Right? So he sends me the key map generated by his XKB common. We reinitialize our XKB common with the same key map. And we are the ones on the client who query these things, right? So the compositor actually sends us the evdev key code. That's what the Wayland compositor sends. And the Wayland client is the one who's responsible for converting that into a key sim and then a code point and then printing that to the screen however he wants to print it. Which, you know, you would think it shouldn't be this complicated. But it is, right? So it's USB device to evdev key code generated by the Linux kernel. We missed a piece in here, by the way. We skipped something. In here, kind of like in here, I guess kind of like right before all of this like input stuff down here. Hold on. We missed a piece. So like kind of like here, systemd gets involved. As always, systemd gets involved here through udev. And what happens is, you know, we were saying that every keyboard will kind of say, these are the letters that are, you know, on the keyboard according to a US English keyboard. But sometimes they get it wrong. And when they get it wrong, people will commit to the systemd the systemd repo, just like remappings of keys for random keyboards, right? So they might go like, hey, this like, I don't know, SVN notebook PN W6567SD, if they click the button A0, they actually meant the mute button. And if they click A2, they actually meant the play pause button, right? So like there's kind of this like low level remapping that can be done, and these evdev APIs allow you to change the mappings. So there's this like kernel call that you can do. There was like EVS something 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 something. Let's see if we can find it somewhere. Do I have it open? This one. EVIOS key code. So for every device that emits input events in the Linux kernel, there's an API you can say like, hey, if they tell you 4, just like actually say 5, you know? So what happens is like, systemd is sitting here monitoring for everybody to get plugged in, and he goes, I've recognized this Dell computer, and if you're this Dell keyboard, like change all the fucking mappings. Like we're gonna go through and change them all. So right, we go USB HID to evdev, kind of through like systemd and udev as like a configuration daemon. But then, then we kind of bypass this later because the kernel will output the right thing. The compositor reads these evdev device events and send those evdev key codes directly to the Wayland client. He, who has gotten a mapping of how those relate to XKB key symbols, earlier, through like some configuration, and he converts those at every key press using XKB common on his side. That is the flow. Yeah, I just thought that was interesting and confusing enough that it's kind of fun to just do a quick little here's the flow. And so probably tomorrow we come back and we implement keyboard handling in the client, or in the compositor and the client. Wouldn't that be fun? Wow. So yeah, thanks for watching, guys. If you want to see that, swing back by tomorrow, or keep up on the YouTube. Yeah, cool. That's it. Thanks for watching.